the idea is to make the contents available to interested parties afterwards, after the project. And as you can see, we've already started recording it. So just to give you an overview of the of today's of what we're planning today, the program itself is divided into 3 parts, I would say. The first part, which we're doing now, the welcome and the introduction from myself, of course, from the project officer and from the project coordinator. The second part is about the resist innovations, where we will take you through the different components and modules of the resist system, as we may put it. And immediately after the coffee break at 12 o'clock, we will present to you the system validation and results, because obviously this system has been validated at 2 pilot sites in Greece and in Italy. And I think it will be, I mean, it's very nice that we can give you an overview of how the system works in real time. And then we'll have a 10-minute question and answers, and then the closing remarks from the project coordinator. Thank you very much. And without further ado, I would kindly ask Mr. Sergio Escriba, the project officer of the Resist project, if he can give us some welcome words as well. Over to you, Sergio.
Thank you, Wally, and to all the participants to join this conference.
We cannot hear you.
No? Okay, no. Strange. 1 second.
No, we
Yes.
can.
I think we can. We can.
Okay, okay,
So,
good. Good.
Wally, should be your speakers.
Yeah. Sorry. I apologize. I put it in such a way that I can speak, but I can't hear what others are saying. Apologies for that. Please, over to you.
Don't worry. So I'm just going to use a couple of minutes, because the interesting part of the day is, of course, the presentation by Resist partners. But just to tell you that from as a project officer of this project, I have had the pleasure to work with an excellent team of researchers working really on the cutting-edge technologies, aiming to increase the resilience of transport infrastructures. And this project was part of a call in Horizon 2020 from 2017 already, and was one of the first projects talking seriously about resilience. So one of the first tasks that you had to make is to really to have a common understanding of what resilience means. Now that word resilient is embedded everywhere. You have seen that many recent EU policies about adaptation to climate change use the resilience concept as something to be achieved, and within Resist you have, let's say, developed solutions to really improve the way that the infrastructures are facing climate change events, extreme events, and also man-made events. In other cases, it's also evident that there may be mobility disruptions due to accidents, to terrorism attacks, or to any type of, let's say, events that are beyond climate change. So for all these events, Resist has been working, developing a set of sensors, monitoring systems, communication tools to gather data from these innovative sensors, then also assessments of the state of the infrastructure based on data gathered through these sensors, and finally recommendations for the infrastructure owner on how to address those events, how to prevent them, and how to mitigate the potential consequences. So, and on all this, let's say the whole cycle of improving resilience, we are going to see today solutions. I would not like to close my intervention by saying that resilience is still embedded in the research programs. In Horizon Europe, you have seen already a topic talking about this increase of resilience. So I invite the developers here to really continue moving these technologies closer to the market on those funding opportunities for research. And for those systems or techniques that are already quite mature and that are ready for deployment, then we have other instruments, for example, Connecting Europe facility, for which there is a call in September this year, to which infrastructure managers can submit applications in which innovative technologies, for example, those from Resist, can be embedded and will be for sure an added value. Well, for this, I just want to thank you again for your attendance, for the organization of the event, and wish you a successful event. Looking forward to know more about your final results. Thank you.
Thank you, Sergio, for these words and for the encouragement as well. Indeed, it's resilience is a very, very important aspect, and we hope to be able to take this system forward in the next calls. Thank you very much for that. And the next item is the next presentation will be given by Dr. Angelos Amtidis from ICCS. Dr. Amtidis is the project coordinator of Resist, and he'll give us an overview of what Resist is all about, and for the benefit of those that don't have just coming to know about Resist, and of course as a reminder to those that have been following this project since the beginning. Over to you, Dr. Angelos.
Thank you very much, Alejandro. Thank you for this introduction, and I'm very happy to be here with you, even digitally. We are at the end of a very interesting but also challenging journey with Resist, and we are actually had to face all the problems with the pandemic for a project that had to do live testing and demonstration. It was not the easiest case, but with the support of all my colleagues in the Commission, we managed, and we are here today to explain to you a little bit on the basic aspects of the project, as it was mentioned already. Allow me to start by thanking FERL, ICCS, and all the consortium for organizing this event, even if it is unfortunately digital, not physical as we wanted at the beginning, as still we are in the aftermarket of the pandemic. And I hope that this will be the last of it, because we are hearing some disturbing messages, actually. I would like also to thank very much and sincerely Sergio and the European Commission for the excellent cooperation we had all these years, and for all the support we had from their side. So I will give you a little bit speak with you on the issues about the project, to give you a first introduction. And of course, later on, my colleagues will give you more details on all the components. And as Adhol said, at the end, we're going also to speak about the validation results, what we have done and what we have seen with the project tools and methodologies. Next one, please. So just to give you an overview of the project itself, we are speaking about a project that was funded under Horizon 2020, under the call MG71 2017. It has to do with resilience, actually, as Sergio mentioned already from that time. Resilience had become more and more, and unfortunately, this came also from some accidents we had. Resilience came more and more an important aspect for the basic and important infrastructure of Europe. And this is still the case, actually. And that was an action on research and innovation. It had a duration of 46 months, so we are ending just now, this next days. And the Commission supported the project with almost 5 million euros. We have been proud to be the coordinator of this project, coordinator of a consortium of 17 partners from 9 different European countries, and with including 2 infrastructure users, which is of course the basis and the important part of every project of this type, because you need the users in order to understand both the requirements but also the results of what you have created. Next one. In this slide, you may have an idea about all the different countries involved and the distribution of partners in these 9 countries I mentioned just now. And in the next slide, a few things on the actual concept, why we did resist. Even though we have seen great achievements in the field of transportation and construction of impressive infrastructures, such as bridges and tunnels all over Europe and all over the world, what we have seen and we have witnessed actually is that they are still vulnerable and susceptible to extreme events that may put human lives in danger. These events may be caused by natural causes like earthquakes, flooding, or high winds, or physical causes like mechanical impact and stress, but also, unfortunately, due to man-made incidents and accidents, or even terrorist events or cyber attacks. Next one. So to address that, Resist actually came up with three main objectives. First of all, and most important of all, is the user protection and the provision of seamless mobility, avoiding human and financial costs. Then the prevention and prediction of extreme events through vulnerability analysis and risk assessments in order exactly to increase resilience. And last but not least, to be able to react to extreme events and provide the optimal information to all involved stakeholders in order to minimize the impacts of these events, and at the end of the day, restore the services as soon as possible. Next one. And to manage these objectives, the project worked on a number of innovations. And I can mention here the custom aerial robot or drones that we have designed and developed inside the project for inspection of bridges and tunnels, and also for being the platforms of different sensors, for mounting sensors on them. Ultrasonic sensors, computer vision systems suitable for drones, and many others have been part of these sensorial suites that we have used in the project. Then we have worked on a secure and resilient communication system, because in many cases we have seen that after such events, one of the first things that fail is exactly the communication system. Then we have worked on a cross-layer cybersecurity solution in order to be able to address cybersecurity threats. Another important module that we have done within the project is the mobility and continuity module and the associated mobile application for passengers and freight movers under extreme events, so they are informed and they can find other solutions in order to continue the service. A vulnerability and risk assessment and a management tool for extreme events. And finally, the center of it, if you like, the core of it, an integrated resist platform called Esthesis, where all components have been integrated in order to provide a holistic overview and an orchestration at the end of the day during the management of extreme events. Let me give you also a few hints on the project architecture, on the main components of the project. As you see in this slide, in the upper right side, we are showing actually the critical infrastructures, bridges or tunnels, and the data coming from existing sensors. On the left side and the upper part again, we have demonstrated, we have inserted the different aerial robots, drones that we have been using in order to inspect the infrastructure and to collect data through the onboard sensors and cameras, as well as to mount new sensors on the infrastructure itself. In the middle, you can see the communication layer that is implemented through the REDCom module. And in the lower part, there is the application layer that includes all the applications that I briefly also mentioned, such as the tools for sensor data monitoring, the vulnerability assessment, the mobility continuity module, the mobile application, and all the other things that we have created inside the project. There is also a cross-layer cybersecurity awareness tool aiming to detect the cyber threats and to prevent relevant attacks. As it was mentioned already, in the next slide, you will see also the validation, what the project did in terms of validation. So the whole system has been validated in 2 pilot demonstrations at the premises of the 2 end users of the project, so namely the Egnatia Motorway and the Technositov site. And I have to say it here and to thank all our partners for the effort they did. It was not the easiest thing to do this whole testing under the pandemic conditions and the difficulties we had to face. But I think at the end of the day, we had quite successful demonstrations. More specifically, the first pilot was conducted at the bridge T9 and T11, located close to Metsovo city in northern Greece, while the second pilot took place at the A32 Milareus Viaduct and the St. Petronila tunnel near Turin in Italy. Both pilots were very successful, as the performance of the resist systems, I'm happy to report to you, was very good, and all components resorted to valuable results. Some of them will be shared with you later on this day. So having said that, let's move on now with a brief presentation of the different resist components that I briefly mentioned. And then we can see more details about the pilots themselves and the results I mentioned in the last part of this event. And as my colleague mentioned, we're going to have also the possibility for some discussion later on. Thank you very much for your attention. Welcome to this event, and thank you for being here with us.
Thank you very much, Dr. Amdidis. Thank you for this presentation. Very clear and straight to the point. Thank you for that. And of course, you've also done part of my job for me, because you've introduced the next stage, which is the resist innovations. So I kindly ask Anastasia to please present the platform and integration environment. So the next 7 slides will be about the resist innovation, starting with the resist platform and integration environment. Thank you.
Okay, hello from my side. I am Anastasia Garbi from European Dynamics, and I will take you through this integrated platform that we have created in Resist. First, I want to present the technical side of the architecture that Angelos presented just now, and to understand how this has been implemented. So this architecture is basically composed of 2 big parts. The left part that is focusing on data collection.
Anastasia?
Yes?
Can you put it on slide presenter mode?
Yes, you cannot see?
At least I cannot see it. I don't know about others, but
No,
we can see the first slide, the full, let's say, presentation environment. Maybe you should switch screens.
I guess you're using more than one screen. That's why.
Okay. Let me then switch off the video. Sorry for that. Is it working?
Not yet. It says you started screen sharing, but at least I cannot see anything yet. Okay.
It's working.
Yes, it is. But if you can put it in presenter mode, if that's possible. Okay. If not, then we just.
Okay. It's okay. I'm glad it's working. Okay, on the left.
It's still not on presentation mode. Maybe you need to share your whole screen, not just the window.
Let me try this. Is it working now?
Loading. Let's wait a couple of seconds.
Okay.
Okay, good, finally. Okay, so this is the technical implementation, let's say, of the architecture that Angelo saw just before. So as we were saying, the architecture is composed of two big parts. So the data collection components that are on the field. So we have two parts of measurement components. So the fixed sensors that are continuously monitoring the infrastructure and provide the information to the STC's platform, and the components, the measurement components that are mounted on their pass on the drones that go to gather data on the field as requested. This data is then stored in the local station, ground station, for which also manage the operations on the field, and they are also processed by the photogrammetric and cognitive computer vision modules in order to analyze the data preliminary before storing them on the system. On the right side, we have the backend system, the backend components that actually take the data that has been collected and stored on this STC's platform and process them accordingly, or provide the user interface for visualizing and interacting with it. The STC's platform is a data broker component, which has this operation to gather data from one side and provide it to the other side in the requested format. There is a quick image validation application which allows to go through all this data that is stored in STCs and check them by mission and by infrastructure with the accessible, taking into account always the user rights. Then we have the photogrammetric visualization that restores, represents a virtual reconstruction of the infrastructure and depicts there all the identified areas of interest that can be further analyzed with the other tools that we have included there. The structural vulnerability assessment and risk management module then considers all this data that is collected, considers the historical data that have been already pre-existing in the infrastructure, if any. There are these external sources where this component takes additional data and helps to the day-to-day monitoring of the infrastructure and analysis of the vulnerability status. This will be presented in detail later. And then we have the mobility continuity app that is the mobile interface, let's say, to interact with the road drivers and help them to understand, inform them if there is a problem on the road, and help them to find alternative ways of driving through their areas. There is also integrated the user behavior module that analyzes the road drivers' behavior and considers this analysis for the communication with them. The cyber security assessment module is monitoring all the backend operations, ensuring that there is no threat or attack involved in the system. And then we have the user management side, the user interface side, which includes also a process monitoring app that includes a workflow that manages the whole mission operations and ensures that all the agents, humans, and systems are informed and involved in the area at the time of the mission where they are needed. The integration environment has been implemented based on the open source development platform that we have in European Dynamics. It's called QLAC, and it offers a modern Web 2 web environment, which provides some common functionalities, avoiding further new development, and ensuring that the fast development of and integration. The web desktop simulates a desktop environment and provides a way to reach all the different and heterogeneous applications that have been developed in the project. There is this data integration aspect that is implemented with the STSys platform, this kind of data broker component platform. There is a full configuration of the environment to meet the specific needs of the user, and the integration is quite easy. You can integrate components of the fly without needing to stop the system from production. This is a view from the integrated environment with the various applications open. So you can see the monitoring components, the mission planning component here on the bottom, the photogrammetric reconstruction of a tunnel, the mobility application, and the content visualization tool that informs about the content of the data that is involved. So I have presented the STSys briefly, but I just want to say that this is the platform that collects all and stores all the data that is coming, as you remember, from the architecture from the left side, and provides them to the various applications for processing. This is a screen that shows how the owner of the platform can check what are the fixed sensors installed and what are the data gathered there, and briefly check them out with this quick image validation screen. So you can check the images, for example, that are gathered during the missions with their pass, and inform if there is a need to go to a specific area with a specific measurement request, and send the drone during the operation again. For this procedure that I have described, so the actual inspection process, we have defined a detailed workflow, like you see here, that involves all the actors that are in the field and at the back end. So we have the control operator who initiates an inspection and provides a flight request and flight plan. The AirPass operator which accepts this request and defines the flight plan and organizes the mission on the field. The user of the photogrammetric vision system, which collects the images from the AirPass and analyzes briefly on the field to provide to ensure that everything is okay. The control before they are stored on the SSS for further processing, and the control operator who is notified that the inspection is progressing, the flight plan is approved, and at various stages, let's say, he has to be intervened. So this shows the complete detailed process that takes place when we need all the measurements that are possible from their past to be gathered. And this is basically the second step, but I wanted to show it in more detail because it's the more complex process that has been implemented. And the quick image in the quick inspection process is supports the preliminary visit of their pass when there is a need for a periodic or emergency situation to explore the situation of the infrastructure, This is goes with a simple air pass that has a stereoscopic camera to inspect the whole infrastructure and collect these first images. So it is a shorter process. This is a screenshot of the system for the process management. Depicts, let's say, this workflow that I presented in more detail and allows the control operator to monitor the process at any stage, though it is actually executed and inform during the execution at what stage of the process the task is available, and informs each operator or each of the actors when they have to perform a task by email. So that's an overview of the platform and the integrated environment. Thank you for your attention.
Thank you very much, Anastasia, for this presentation. We now go to the next one about the Redcom communication model. We heard earlier from Dr. Armidis about the fact that when, for example, there's an earthquake or something, obviously one of the first things that disappears or disconnects is the communication. So we're looking at this Redcom communication model that will provide secure and continuous communications. Can I kindly ask Yashon Somarakis to give us this presentation?
Actually, for the Redcom,
no, Vole, this is Manolis from Fourth.
Oh, sorry. My apologies. Manolis.
That's okay,
I beg your pardon. Sorry.
Let me share my screen. Okay, I hope everyone can see my screen now.
Yes, perfect.
Okay, so I am Manolis Michalos Dimitrakis from Fourth, and I will be presenting the Redcom. Okay. Why is not changing? Do you still see the first slide?
Yes.
I think it's stuck. Let me. Restart it. Okay. Okay, now do you see the second slide?
Yes, we do.
Okay, now it's okay. So what is Redcom? Redcom stands for Rapid Emergency Deployment Mobile Communication Infrastructure. The main objective is to build an infrastructure to support and handle communications in emergency situations when standard communications networks are not available. For example, if we have an earthquake and we need to conduct inspections on a bridge, we need to have a communication infrastructure that can provide means for involved parties to communicate. This communication can be internet access, radio access, or cellular coverage. So what we did was to build a trailer that we can move around and put in this trailer equipment necessary for the communications. So first of all, how do we power the Redcom? The Redcom power supply is provided by an inverter. This inverter has 4 available options. First, of course, is the external power. Second is a petrol generator. Third is a wind turbine. And fourth are solar panels. The solar panels and the wind turbine charge 2 batteries that are connected with the inverter. The inverter, the batteries, and the generator are inside the Redcom trailer. The wind turbine and the solar panels are mounted externally on the trailer. Regarding the network deployment of the Redcom, we have 3 options for Ethernet access. We have an LTE modem which uses SIM cards to provide internet through cellular data. We have satellite modem to provide internet through satellite. And also we have several access points that can be used as clients to receive internet access wirelessly from another wireless station. Of course, there is also the obvious option to plug in an Ethernet cable. Additionally, on top of the Redcom, we have an IP camera that we can use to view from a higher ground, and also a GSM base station that can provide cellular coverage to mobile phones in the nearby area. The access points, the camera, and the GSM base station are mounted in a pole that can reach 9 meters height. This pole is retractable for easier transportation. Inside the Redcom trailer, we have installed a server powerful enough to host all the Resist platform. This server uses the Hyper-V as a hypervisor, and all the Resist components are installed in virtual machines in this server. Having all this inside the Redcom offers faster transfer speeds. Additionally, having all the virtual machines enables the use of a global intrusion detection system. The Redcom has two compartments. In the first compartment, we have the inverter, the generator, and the chargers for the wind turbine and the solar panel. In the second compartment, we have a rack, and inside the rack, we have the server, the monitor, the modems, the router, and the switch that are all connected with. How the Redcom fits with the rest of Resist components. As I have already mentioned, the server with all the virtual machines that run the rest of the components is inside the Redcom trailer. The drone, the ground station, etc. are in direct communication with the server via the Redcom. This is how the Redcom looks like. And on the right picture, we can see the Redcom deployed during the first pilot in Egnatia Odos. Thank you very much.
Thank you very much, Manolis. Thank you for that presentation. And now we go to Yason Somarakis. So apologies once again for calling you earlier than necessary. And Yason will be talking to us about the cybersecurity model. Over to you.
Hello, everyone. I'm Yason Somarakis. I'm a security engineer in Sphinx Technology Solutions. So today we are going to see the cybersecurity framework implemented in Resist. A few words about the presentation. First, we will have a summary of the features, then the placement of the framework in Resist, of the various components of the framework in Resist, and the added value and the benefits, and finally some screenshots of the views of the components. So, the cybersecurity framework can be seen as a collective of two things: the cybersecurity mechanisms that are responsible for identifying, mitigating, or preventing cyber threats, and the cybersecurity assurance mechanisms that are responsible for reactively and proactively identifying cyber threats. The security mechanisms include an intrusion detection system, cryptographic mechanisms that are used to protect the communications, for example, between the backend and the field, resilient communications via redundant channels with the Redcom, authentication and authorization of users and resources. And cybersecurity assurance mechanisms involve, first of all, the modeling of the cyber system. This allows us to create tailored security assessments specifically for the needs of Resist and its assets. And these assessments involve direct and indirect vulnerability assessments, penetration testing assessments, and continuous monitoring assessments. So a few things about the placement of the components in Resist network architecture. We have the intrusion detection system in the backend. We have the resilient communications across all communications in the field. We have cryptographic operations between the field and the backend on sources or users. We have authentication and authorization of services and users. And we have the security assurance platform that monitors evidence from these security controls and more to give you an overview of the security posture at any time of resist. So what's the added value? Regarding the cybersecurity mechanisms, we integrated various security mechanisms based on a threat analysis that have been conducted early in the project that gave us a clear view on what's needed in the project. And to implement those security mechanisms, we used off-the-shelf modules like the hardware keys that we used for some cryptographic operations, or other modules brought by members of the consortium, such as the Cloud Ids system brought by Forth, or the early warning intrusion system, again brought by Forth, the AirPass encrypted communication implementation provided by use, and more. Then the cybersecurity assurance mechanisms are there to model resist and illustrate what's the status of all assets in resist, so that vulnerability assessment and penetration testing can use this information to perform tailored scans and assessments, both static and dynamic. And then the continuous monitoring assessment that integrates tightly with the various security controls to collect specific evidence, observe services from various sources, and determine specific security objectives. A few examples of the security objectives that we're covering are the availability of internal systems in the backend, if, for example, a VM is up and running, the availability of specific security controls, such as the intrusion detection system, the integrity of the results generated by the security controls, by the IDS, potential abnormal access attempts on the system, and some deauthentication jamming attacks affecting Wi-Fi networks. That's especially useful in the field. Some screenshots now about the components. This is the dashboard of the Cloud Ids. Here you can see a figure showing the types of attacks and a number indicating how many attacks are happening per source IP. This is a Cloud Ids. It's important to say that it's deployed on the hypervisor level. It has an overview of all components in resist. Moving on the early warning intrusion system. This is basically a honeypot that passively captures traffic and gives us nice indications about origins of the attack in terms of country, IP, packet type, protocol type, sorry, and some other interesting statistics. Then moving on to the assurance platform elements. This is the view of the overview. Here you have an overview of the assets in resist, and this is a more thorough overview, a table that illustrates some more details about each asset, and you can also browse each asset and explore it, and also create new assets. And then we have the execution view, that this view is used for the assessments, to perform the assessments. Like I said, we performed 3 types of assessments at this time. And per assessment, we have specific results generated from it. Each result view has some specific metrics. For example, in this screenshot, you can see the results per severity, or the most vulnerable assets that have been assessed in this assessment. And also in each result, you can see in each assessment results, you can see a list, a comprehensive list of all the results included in the project, in this assessment. And for each specific type of assessment, we also have some in-depth information about each result. For example, for the vulnerability analysis, you can see the common vulnerability enumeration information presented there, and yes, and the base score of it. And for penetration testing, you can see some more technical information, such as where does this service run in terms of networking or technical impact, sometimes a mitigation description, and other technical insights. Finally, for continuous monitoring and based on each scenario, you can see a violation or satisfaction. In this instance, you can see a violation of the availability service, and this is illustrated as here as a violation. And thank you. This concludes my presentation.
Thank you very much, Jason, for that presentation. The next presentation is on the aerial robots and ground control stations. So we'll be looking at the inspection and the mounting of sensors of bridges and tunnels, and of course the ground control station as well. To do that, I would like to kindly ask Miguel from CATEC and Guillermo from University of Seville to please give the presentation.
Okay, so yes, good morning. Yes, one thing that from CATEC it will be Jose Ignacio Morillo who will give the presentation, and myself, Guillermo from University of Seville. Okay. So next slide, please. So here, what we are going to present are the main innovations that are in the resist aerial robots and also in the ground control station. So as has been mentioned, the main objective of the aerial robots is to carry the different sensors that allow to gather data on the state of the infrastructure. Related to the ground control station that is used to control these aerial robots, the innovations are related to mission control. Then, with relation to the visual inspection robot, there's the innovations are also related to the autonomous mission. The main innovations are in the aerial robots that are used for contact inspection, just to carry the sensors that need to be in contact with the infrastructure to take the measurements. And also the localization system of these robots that we will present for bridges and then for tunnels. And now Jose Ignacio will present the ground control station and the robot for bridge inspection. We cannot hear you.
Can you hear me now?
Yes, no, it's okay.
Okay, sorry. Hi, good morning to all. I'm Jose Ignacio Murillo from CATEC, and I will start presenting the aerial robots for bridge inspection and the ground control station. Okay, so let's start with the ground control station, which is composed of two main modules. The first one is the mission control module, the GCS engineer, that allows to the operator to manage the inspection and to see different important information like the drone path, system status, and the mission status. And the second one is the pilot interface, the GCS pilot, that shows to the pilot information like the first person view video from the drone, the obstacle detection, and the general status. And here is a video showing the engineer GCS in a visual inspection operation. Is the drone path, the autopilot and LiDAR information, and the mission status information. And in this video, in the left you can see the LiDAR point cloud, and right we can see the GCS pilot video. And when we are in front of the bridge, we are going to see that the obstacle information is showed here. Okay, so now we can see it. And there is in left picture, we can see a visual inspection robot. Middle picture, we can see the contact inspection robot. And in the right picture is an example of what could be the bridge where we inspect, in that in this case is the Egnatia O2 bridge. Here we can see again the bridge from another point of view. And this is the setup needed for the inspection operation. Okay, so in this slide, you can see the list of components belonging to the visual inspection robot that is using the stereo camera system. It is a commercial drone with multiple adaptations. It has a gimbal for camera orientation and stabilization, and in this gimbal, it is situated the stereo camera system. It has vibration dampeners to avoid the vibration in the pictures, and electronic covers for dust protection. The LiDAR under with different configuration depending on the field of view, and onboard a computer for custom flight control, and a commercial autopilot with advanced SDK interface. We can see the GCS engineer during the mission generation for the visual inspection drone. We can select the desired surface in the bridge and the waypoints that the drone used for the navigation are created automatically here. And this video shows a complete mission generated. Now here is a video of a takeoff that is fully autonomously. And then a video from the robot executing the operation. Okay, so now let's move to the contact inspection robot. That is a CATEC technological base. Is an aerial robot with contact capabilities with a new design. The new design has a weight and size reduction of 40%, which allows to develop a safer and easier operation. It has a new octo-quad configuration, more powerful and compact than before. And it has some modification on the robotic arm that improves the autonomous control. And the sensors on board are the ultrasonic sensor, the cloud width sensor, and the permanent vibration sensor. In this video, we can see the contact inspection robot reaching the surface. In this part of the operation, the pilot is controlling the drone. Okay, so when the drone contact to the bridge, this part is fully autonomously. So the final effector is in contact, and the operator can command the direction in which is necessary to move. In this video, it is shown the permanent sensor installation. You can see here in green. We can see now a little bit closer the permanent vibration sensor that I presented before. And in this video, we can see the ultrasonic sensor taking measurements in real time. And here's a photo of the category system. And that's all from my part. So I let Guillermo continue And thank you so much for your attention and your time.
Okay.
Thank you very much. Guillermo, you still have a presentation, I guess, right?
Yes.
Okay, please.
I don't know if you can see it.
Yes, please.
Yeah. So now I'm going to present the aerial robots that we have developed in the project for tunnel inspection. So the idea is that the environment for inside a tunnel, it's very different from that flying close to or below the bridge, and also the conditions of the surface that we have to inspect. And this is the reason that we have developed different concepts for the robots, especially for the contact inspection robots. So similarly to what Jose Ignacio has mentioned, for tunnels, there's also a visual inspection robot, a contact inspection robot. You can see in this photo the prototypes, the robots that we have used in the pilot in the Santa Petronila tunnel. Here is the visual inspection robot, and this larger one is the contact inspection robot that I will discuss later. And this first one is a smaller prototype that we use for testing the control and localization systems. Okay, so for the visual inspection robot, the design is similar to the one that Jose Ignacio has presented. It has the camera and the platform for the directioning it to the different parts of the infrastructure. The main difference is that the sensors that are used and the localization system that it uses the special localization system for tunnels that I will present later. Okay. And for the inspection robot, this is a different design. In fact, it's a very new design that is able to contact the tunnel walls, the curved tunnel walls in each part. So it is designed, you can see, to be able to touch in any part of the 90 degrees from vertical just to horizontal in the top. And then when it is touching you can see here at the right, the small card with the sensor can sweep on the surface just to take surface 2D measurements or linear measurements, and also it can be used to fine tuning or just reaching with high precision the point or the crack or the defect that we want to inspect with the say ultrasonic sensor or other sensors. So it is able to mount different sensors that has been developed in the project, and you will see in the next presentation. The design, you can see here the design of the and the movement of the platform. And this is the card that has the sensor mounted on it, so it can move along all the surface. And there is also really sorry. There is also another degree of freedom that allows to adapt this to the different curvatures of the inside walls of the tunnels. Okay, and with this, it is possible to touch in every point of the surface of the tunnel. You can see here one of the experiments that we did in Santa Petronila tunnel, here in the left, you can see the robot, and in the right, you can see a small camera that we put on the card just to show that it is just sweeping on the surface. Okay. Then for the localization, so it is an important point for any robot, but for other robot it is even more important. And inside tunnels, it is also critical because it is not possible to use the GPS or GNSS signals because it is there are no satellite visibility. Okay? And also other usual other techniques that are used normally in robotics, like vision or leader-based SLAM, fail in many situations because of the symmetry of the tunnel. So the longitudinal symmetry of the tunnels makes that it's very difficult to find reference or significant points that can be tracked from one image to another. So we have developed a mixed localization for the aerial robot in tunnels that do not use the GNSS satellite signals, and we use two LiDARs, 2D LiDARs that are just sweeping the area in the transversal in the vertical plane and also in the horizontal plane. And using this, and then also ultrasonic range sensor for longitudinal positioning, these onboard sensors give an estimation, or an absolute estimation of the position of the robot. But we also merge with the information from a total station that is able to track the position of the aerial robot, and then with merging all of this, we can get a very precise estimation of the very precise localization of the robot. You can see here how the localization system works. You can see that this is a 3D point cloud map of the tunnel, and you can see to the right how the sensors, the 2D lasers, are detecting the profile of the tunnel, and then by adjusting this to the known profile of the tunnel, it is possible to to know the exact location in the vertical plane of the robot. Then, of course, in tunnels, it's also important, and especially for large aerial robots like this, the control, the autonomous functionality, especially for robot control. So it is important that all to model and just take into account all the interferences, aerodynamic interferences of the airflow from the rotors with the tunnel walls, and also the contact force that generates whenever it is touching the tunnel wall. So this we have incorporated this in the controller, and just to make us the movement very precise. Okay? And that's all. This is the thing that has been making the experiments in the Santa Petronila tunnel for University of Seville. So,
thank you very much, Guillermo. Thank you, Jose. Thank you for this very interesting presentation. We've heard so much today about sensors, and I think it's now time to look at the types of sensors that have been used, and of course, the computer vision system that have been adopted, which is which needed to be suitable for the aerial robots. So the next presentation is on ultrasonic sensors and computer vision systems. And it's the presentation will be presented by Luca, by Raphael, and by Ramesh. Please, the floor is yours.
Thanks. I'm going to share my screen. Can you see the presentation?
Yes, please, Luca.
Okay, thanks. I'm Luca Belsito. I work at the National Research Council of Italy. I'm going to introduce the measurement that we perform and that we have integrated on the Factor and the RESIS project. And then the colleague for vision will introduce the vision part. Basically, with the RESIS platform, we can perform ultrasonic measurement. These ultrasonic measurements are in particular crack depth measurements and evaluation also of the Young modulus, crack width measurement as well as an alternative solution to vision, and we have designed a low power vibration mode with the sub-gigahertz communication. Here is the idea you can see on the top for the crack depth measurement. It's a standard technique. We use two piezoelectric transducers, one on the left, one on the right of the crack, and we generate an ultrasonic wave. This ultrasonic wave propagates across the concrete, is reflected from the bottom of the crack, and then is detected by the receiver. By measuring the time between the emission and detection, we can determine the depth just by plotting simply the Pythagoras theorem. For the crack width measurement instead, we use an indirect optical phase measurement like an optical profilometer that we scan around the crack to determine the width. And finally, we will see the design of the low power vibration module. We looked at the market, but finally we decided to design a custom pulse receiver unit to have the possibility to easily integrate the platform on the drone, to have a USB communication, also to have the possibility to choose the actuation frequency and also the voltage, the driving voltage. This custom pulse receiver unit that we have developed can generate driving voltage up to 3000. This is really important in the depth measurement, the crack depth measurement. You can see on the right the integration of the piezoelectric transducers on the two different factor. One on the top for the bridge spector, where we use two 54 kilohertz transducers that are visible in red, and on the bottom, where for the tunnel spectrum we use smaller transducers. The ultrasonic measurement, we have performed several measurements during the different trial in the Tinovo Bridge in Mesovo and also in the San Petronila tunnel. We have an application running on the ground control station. With this kind of application, we can set all the measurement parameters, like I was saying before, the actuation voltage, the resonance and frequency, and so on. And we have also inside the pulsar a really high resolution time to digital converter with the 55 picosecond to really precisely measurement the time between the emission and detection. And here we can see, for example, an acquisition of the acoustic wave during the Mesovo Tinovo Bridge, where the signal is really clear with a really high to signal to noise ratio, where we can measure exactly the time on flight and determine the ultrasonic speed or the depth. In this kind of measurement, we have used an actuation voltage of 2 kilohertz. We can see now the integration of the crack width measurement system. As I was saying before, we decided to use an indirect optical phase measurement. We use basically a modulated laser source that's used to interrogate the target, and we measure the optical power reflected from the target by using an avalanche photodiode. By measuring the time between the emission and the detection, we can precisely determine the distance of the target. Scanning this kind of system around the crack, we can perform the crack width measurement. We have successfully tested the system and measured the crack down to 0.4 millimeter. And on the right, you can see an example of a measurement where you can see the profile and the width of the track measurement. With this kind of system, we have a resolution of 0.1 millimeter in space, also 0.1 millimeter in depth. Finally, we have designed this vibration measurement module. This module employs a 3-axis accelerometer from analog device and transceiver with a microcontroller integrated from Texas Instrument. In the design, we try to realize something that is interoperable on the factor to be attached on the structure to measure the vibration of the structure. So we have a system really light with a weight less than 40 grams and the diameter of around 50 millimeter. The signal to noise ratio of this kind of accelerometer is really good. We have 20 micro G for square hertz with a bandwidth of 1 kilohertz. And it's designed with a really low power consumption. We can have a continuous transmission of the data and acquisition of the data on 3 axes for 72 hours. And of course, it is for continuous transmission, but we want to have an intermittent transmission of the data. The battery life can be also much longer, can be longer than months. Also here, it depends on the timing of the measurement. The transmission is wireless with some gigahertz communication, so we have many vibration modules that can simultaneously communicate with the on-ground receiver with a communication longer than 150 meters. And here we can see, for example, the installation of the vibration module performed from the end effector. This vibration module is installed on the structure by using an AV curable glue with a really good transmission of the mechanical vibration. And by exploiting a user application on the ground control station, the user can set all the measurement parameters, like, for example, the acceleration range, the cutoff low pass frequency and pass frequency, the sampling frequency, and so on. After the installation, the module starts communicating with the receiver. Here we can see the acquisition of the data, for example, during the Masovo in the Tinovo bridge, where we have on the top the real-time acquisition of the acceleration, and on the bottom we can see also the fast Fourier transformer of the data, so the vibration mode of the structure. And during the trial, we have also acquired the data by using a permanent wired sensor to compare and validate the data. That's all on my side. Now, Rafael will continue for the vision part.
Hello. Can you hear me?
Yes.
And see my screen? Hopefully, yes. Looking good.
Yes.
Okay. So I'm Rafael from the Technical University of Graz in Austria, and I'll present to you the photogrammetric computer vision system. The objective of our system is to capture images of an infrastructure and recover the 3D data in order to gain information about the underlying structure from images alone. So basically, we collect a bunch of images, plug them into our system, and get a 3D model as output. For this purpose, we have developed 3 separate components. Firstly, we have the stereo sensor for capturing and storing images while being mounted on the drone. On the side, we can see a CAD drawing of the sensor design. Secondly, we have developed 3D reconstruction algorithms which generate depth data from the captured images. This enables us to take fast and accurate measurements on the observed structure immediately. And finally, we created a web-based viewer where the user can view the generated 3D model. With this application, the user can get an easy overview of the detected damages as depicted here in the screenshot. I'll go a bit more into detail about these components in the next slides. So as a means for visual inspection, the RESIST system deploys a high-resolution stereo camera sensor. We have developed a custom design to fit the RESIST requirements, utilizing two 12-megapixel sensors with an 11-centimeter baseline. Images are captured and synchronized with a small onboard computer. This computer also collects metadata from the drone, for example, the position. And everything is then stored directly on the connected SSD drive. In this manner, the stereo sensor is a modular component and can interact with another component, in this case, the drone. And depicted here, we can see the stereo sensor integrated on the drone. On the right, an example stereo image as it is captured in the air from the robot. After the images have been captured, we have to generate 3D data from these 2D data. Why is this important? Because it enables us to perform accurate measurements from images alone. And only by doing this, we can show a 3D model depicting the condition of the structure at present. To get fast and accurate results, we deploy deep neural networks for these tasks. However, in order for this to work, we need to transfer the images from the drone to a more powerful system. Our solution here is to use a combination of a laptop with an external GPU as depicted here. With this solution, we have access to the computational power of a high-end graphics card directly on the field. However, some challenges still remain. Firstly, the latest deep neural networks often use multiple graphic cards together, and with our setup, we can only use one, limiting us in memory. Moreover, we are limited in time as we want the 3D data as fast as possible. And reconstruction algorithms on the market can sometimes take hours for processing. Secondly, we want our algorithms to be robust against the difficult and different lighting conditions in the images. Because of course, there's a huge difference if I take an image outside of a bridge or inside a tunnel. And thirdly, of course, we want high quality reconstructions. So in order to tackle these challenges, we conducted most of our research for RESIST in this area and issued the following 2 publications. In 2021, we published our paper, High-Res MVSNet, a fast multi-view stereo network for dense 3D reconstruction from high-resolution images in the IEEE Access journal. And recently, our paper, Atlas MVSNet, attention layers for feature extraction and cost volume regularization in multi-view stereo, has been accepted to the International Conference on Pattern Recognition and will be presented later this year in Montreal, Canada. To show our results to the user of RESIST, we developed a web-based 3D viewer. This enables the user to get an overview of the observed structure directly in the RESIST application. The viewer has several features like completely free navigation, showing annotations of the detected damages, and taking coarse measurements directly on the model. Yeah, okay. And finally, I want to show an example video of the bridge visited in Greece. So this model is a direct output of our software pipeline without any sophisticated post-processing. Of course, we can only reconstruct parts of the images of the bridge that have been observed by the drone. And so in theory, the more pictures we get, the more complete the model will be. And all the data we generate in our module will be passed on to our partners for performing a more detailed image analysis. This concludes my presentation. Thank you for your attention.
Okay, I share the screen. Okay. So I'm going to talk about the computer vision system. Already you saw that the stereo data and it's actually stereo images are taken, and there is a deep learning module that produces 3D data from Rafael. And then the purpose of the computer vision system is to actually analyze the 3D data along with the stereo images, identify defects, and then we have actually a multi-staged process that allows you to essentially have human look at these results, and then it's possible for the human to basically modify the result. And then furthermore, in order to deal with complexity in the particular situation, the human has the option to actually add additional modules. I'll come to that, and then test out options. So in the end, basically the input from the TOGRATs is actually passed on to the computer vision module with certain possible human input to actually then produce the defects along with an XML file, which is then passed on to the aesthesis platform. I want to make one main point in the beginning of this thing. one of the main aspects for us in this project, there was a talk about resilience and robustness and all these things. In fact, one of the main contributions from our side is actually in bringing our methodology for system design in a principled way to go from context, tasks, and performance requirements in the application context to actually detailed models for simulation, detailed models for machine learning, performance modeling, and so on, and actually then compose actually the modules that can be then flexibly combined, just like a human would do, or at least a human brain does. So in that sense, the system engineering methodology application of it is one of the main contributions in this project. Now, what have we done? We have actually built a flexible toolbox. And you can see that there is actually, for instance, on the bottom, there is a simulation and decomposable sort of machine learning framework that is open source plus our own tools we built. And on top of it, actually very specific modules which address different aspects for the requirements that you have. For example, one of the requirements is that you don't want to depend only on data for analysis, meaning that you want to use models that you can actually have context, and then you can actually design algorithms that don't have to train on large amount of data. On the other hand, if you have large amount of data, you want to use them. So we have a hybrid approach of how to combine modern machine learning with actually system engineering principles to build our system. Moreover, the system is scalable in terms of computation, because what happens is that we have this massively parallel computation for hypothesis generation, followed by deliberation. Basically, this is what psychologists call system 1 and system 2, and how they come together to build a human-like architecture. And then on top of it, of course, you have the software tools, the GUI and the editors, and the transfer and mensuration. So just to walk through it very quickly, first point essentially is you want to use the contextual knowledge in the form of physics-based models and statistical pattern models. These are actually cultural knowledge from science, which is then mapped into particular operators that should be robust. So here, no deep learning is happening. The deep architecture is designed by the expert human based on understanding the application context, the physics of the problem, and the patterns you talk about. That's one. Number two, essentially, is that we have actually made progress. By the way, the color coding, I want to just tell you, the color coding here means that the kind of bright orange, bright yellow is actually extensions that we did from Aerobe for resist and modification. And then the other deep orange, dark, is actually things explicitly done for resist. And then the gray areas are reused from Aerobe. So one of the main issues that we had in this project was the pandemic. So data collection was a major problem in the sense that we could basically, there are hardware delays and so on. So what we had to do was focus on this issue of small sample learning, meaning that you want to only use the information from a single image and then produce actually the best possible result for classification. How do you do that? You can actually use, in fact, you can learn from a single image what actually is the background texture like, as long as you can actually say what parts of the image you think there are hypotheses from the, in terms of cracks and so on. So we combine model-based idea from the previous slide along with modern deep networks, basically build actually an image. This is actually an image constructed by a neural network from this image that shows you actually what the background texture is. And then the difference basically shows you how good, where the actual defects are. So that's actually a very concrete advance since the last work we did. And here is another example of the same thing working in a tunnel case. Now, there's the other part, again, due to the pandemic and so on. One of the biggest issues in machine learning is data collection, the cost of it, and so on. So to reduce the cost of data collection and to also do model-based science and validation, simulation is a very important part. And we actually extended our simulation, and then we used it to basically train our machine learning models. So here you see essentially the kind of simulated data that we have built up, especially for steel bridges, for example, how essentially defects can be, and so on, and corrosion could happen. Similarly, if you have actually concrete with actually graffiti and other moss and other things, we could actually then simulate it by using graphic simulators. And we have applied this. One more innovation that we have done is actually we modified the architecture and come up with a new architecture and applied what's called a multitask unit. So which essentially takes the input image and maps it explicitly to the cracks and then the surface normals and depth from a single image. This complements what TU Graz showed you, which is from a stereo image, how to construct 3D. Here, actually, it's a single image going to estimates of 3D. In fact, the idea that we had was to combine the TU Graz work with our work so that we can actually then make the coupling help you in actually advancing essentially the way in which you do inference of the structure geometry as well as the defects. And that I think is the future work to be done. So we also have tested our simulator that we built on the steel and then applied it on real data set we got from Technositaf to basically give you an idea of what exactly corrosion detection may look like. Right now, this is only tested, simulation is used for machine learning and then testing is done on real. We also did work on extending our idea of topology-based extraction in the geometry side. So we can actually use geometry modality directly from TU Graz, and then we could actually analyze the structure and then find cracks. And the advantage, so the hope was that if you had really complex geometry and complex, let's say complex background texture, it may make sense to directly use the geometry that you get from TU Graz and then get the answer. But the point is that we need to be close enough to take the picture. Otherwise, you wouldn't have the ability to resolve the cracks and so on with geometry. And of course, finally, all these modules get combined, infused, and then you have a GUI, and then you have actually the cracks, and then you transfer it. So here are some examples that we got from the Turin pilot data. We were able to show that the techniques have good sensitivity, and all these modules are useful. And clearly, from a context point of view, if you know the context, you can actually appropriately choose the modules. Similarly, here is basically an illustration of what happened in the tunnel system for the different modules and then combinations. So in other words, imagine it's like a mixture of experts. You have multiple expert modules. They provide you partial hypotheses of what the answer should be, and then we can combine it and fuse it. That's exactly what's going on here. The left two are the guesses, and the right essentially is a fusion. Same example for another example. And then here is another example. And so finally, the main point I want to make is that the field tests confirm actually the system engineering methodology. And it shows that the innovations that we have put in, especially for addressing the small samples and low data scenario, is actually useful. And we need to further improve it and optimize it. But essentially, the key point essentially is that the system engineering philosophy and basically design for safety essentially has been validated in this context. In fact, we validated this together with Aerobe in a way, because this is actually a long-term project for us for the last 6-7 years. And in fact, this has resulted in a journal paper which just came out, which where Martin Mund was one of the early people influencing this platform development. And his paper essentially, and he was also helping in the resist, and the results are now slowly coming out. And we plan actually a very long journal article, which shows the principal design for safety, resilience, and so on. And that would be a major work. We are just starting to work on that and to collect all the stuff, and it's a long effort. And we also had several bachelor's, masters, and other theses just done. Ashraf Jaziri is actually one of the key guys who helped us wrap up the project, even though there were so many delays. And he essentially had a thesis done, bachelor's, now he's doing master thesis both on resist. And then we also had another master thesis, which actually I didn't even show the results on, which is actually checking on neural architecture search and model-based design and how essentially that could play in resist. And we had some insights on how to do descent angle representations of which actually makes it more explainable, the design of these systems. So in summary, I think the resist project has been an extremely great project for us in terms of the collaboration with the partners, and also to verify our systems thinking and systems methodology. And we hope that this would be a showcase for actually the effectively showing the community how to think about principal design of AI. Thank you very much.
Thank you very much to Luca, Rafael, and Ramesh for this excellent presentation. We'll go to the next presentation. Well, based on the robotic measurements, the RESIS has developed the possibility of assessing the probability of structural failure and damage under different extreme loading, earthquakes, explosions, etc. And to give us a presentation on structural vulnerability assessment and risk management, I'd like to call upon Stefanos. Over to you.
Hello, this is Dimitris Villonis. I will make the presentation on behalf of Stefanos and Riza. So may I share my screen?
Yes, please.
I hope that you can see the full slide of my PowerPoint.
Excellent.
Okay. So this is Dimitris Villonis, and I'm going to present the structural vulnerability and risk assessment software that was developed during the RESIS project. The objectives of the structural vulnerability and risk assessment tool were to provide the user with capabilities such as to retrieve and analyze different types of data coming from the Esthesis platform and external sources, to perform structural and vulnerability assessment of the structure's components, to assess the risk of the structure, either regarding individual component or as a whole, to monitor structure's condition, for instance, from inspection to inspection. And our ultimate goal was to make a tool that could be able to assist operators in decision-making regarding tasks such as strengthening and maintenance options and decisions in case of emergencies. The structural vulnerability and risk assessment tool constitutes one of the modules of the RESIS platform and was designed to allow interoperability and communication between the rest of the modules of the platform. The tool is executable in a web interface environment, so it can operate in any web browser such as Google Chrome or Mozilla Firefox, etc. And we can say that it has a pretty user-friendly interface. The main window of the tool has a tree structure at the left side, where the information regarding the elements of stored in the tool are presented, such as the types of infrastructure, bridges or tunnels, the materials, and the cracks or other defects coming from inspections, and of course the list of inspections. And if the user clicks on a tree node at the left side, then some windows open at the right side, and if the user clicks on the editor button, then a new window with the data related to the selected object are displayed. So in this case, we have selected the Egnatia T9 bridge, which was one of the RESIS pilot cases, and you can see the data related to that structure, such as the length, the construction day, and other data. And of course, from this window, the user can edit and modify the data fields. Furthermore, if the user double-click on the name of the structure, then a pop-up window opens with a 3D model of the structure. Each structure may be divided into sub-elements, such as a bridge can be divided into beams, and each beam can be also further divided in beam parts, and those elements are displayed in the tree structure at the left, and the list of all elements can also be displayed in the right part of the window. So we applied this tool by taking information from the inspections that took place during the resist pilots. The first pilot was the Egnatia Bridge in Metsovo, Greece, and the Egnatia motorways gave us some findings from that inspection that took place during last March. And in this photo, we can see the cracks and other types of defects detected in the middle span of the bridge. And in order to store this data into our tool, first we created an inspection entry where we stored all the information regarding that particular inspection, such as the date of inspection, the infrastructure, the structure, which was the Ignatia T9 bridge, and the operator. And then under the node crack, we stored the 10 families of cracks that were detected during the inspection, and we can display the list of all cracks in this part of the application. And if one selects a specific crack, then another window called editor opens where all the information regarding the crack are displayed. And in this part of the table under the tab data, the user may see the crack features such as the depth, the width of crack, the length, and in the two axes, and the type of crack. And I should say that the tool provides also the option to store data from for more than one inspection for the same crack, and this is very useful since it can provide the user with an opportunity to monitor the evolution of the specific crack. And furthermore, under the tab photos, the user may upload and store pictures taken from the spot from the structure with showing the specific crack. In a similar way, the user may store data regarding other types of defects, such as segregation of concrete, etc. And as you can see, the way is similar to that of cracks. Our tool provides the user with the opportunity to store and display deflections in of the structure. For instance, during the pilot meeting in Metsovo, a number of loading tests on the bridge took place, and in this case we saw the deflection result of a loading arrangement number 4. As you can see, in the middle of the middle span, the measured deflection was 12 millimeters, and it is graphically displayed in these figures under the deflection measurement tab. Furthermore, the tool may perform a structural assessment. In our case, we have used the data provided from the inspection, and we can see the risk level of the specific part of the bridge. And in order to visualize the risk levels, we have used the column pattern, and the green color is for low risk level, the yellow is for medium, and the red is for high. And let's move now to the second pilot of research project, which was the tunnel, and especially the St. Petronila tunnel in Italy. Our tool can be applied to a tunnel in a similar way that was applied in a bridge. Of course, if the user double clicks on the name of the tunnel, a pop-up window with a 3D model of the tunnel opens. And in the case of tunnels, we should say that we divide the structure into cross sections along the length of the tunnel. And we can, if we we click on a node under the cross sections in the tree structure, we open an editor in the right, in the right part of the application window, and under specific tabs we can see the data, which is the length of the position of the cross section along the tunnel and the risk level. If we click on the tab viewer, then a 2D representation of the tunnel opens, and also that cross section is divided into elements, and we can also see the risk level of each element, and following the same color pattern as in the case of the bridge components. And finally, under the tab cross-section strains and internal forces, an overview of the strains and the internal forces acting on the selected cross-section is presented. These are pretty much the main features of the structural and vulnerability assessment tool that was developed by RISA during the RESIS project. Thank you.
Thank you very much, Dimitrios. Thank you for that interesting presentation. And so last but not the least, the RESIST project also considered the needs of the highway users and the overall interaction between the drivers and the infrastructure managers. And that's why the mobility continuity module has been developed. And for more information on this, I'd like to call upon Theodoris from ICCS to give us his presentation. Thank you.
Okay, thank you very much, Adewol. So, as you said, within RESIST, we have developed the mobility continuity module, which aims at, first of all, providing trip planning services to end users which are using the related infrastructure. And in addition to that, and what has to do with the resilience, the mobility continuity module provides rerouting in case of road lane closure with support for both vehicle and buses that serve the related area. Moreover, the module provides personalized notifications regarding the road laner, the road or lane closure events, so that the drivers which are using the infrastructure can be informed and take the necessary actions. These messages are accompanied by information regarding the average speed and calculation and the respective calculations, so that there's also, in the case of lane closure, some more information for drivers to have an idea regarding if a lane is congested or not. And finally, another important module is the sentiment analysis based on Twitter feeds, which gives insights regarding the driver or infrastructure and user perception of an event. So these features have been able to be provided due to the subcomponents which were developed within RESIST. So in terms of the backend, as mentioned, one core component is the trip planner engine. Moreover, in order to calculate the average speeds for lanes in terms within the context of a lane closure, we have used the mobility simulator, which was basically a digital twin of the infrastructure. Moreover, we have developed APIs regarding road lane event management. also these APIs are backed by the persistence layer. The persistence layer, which holds user data road events. And of course, we have some other technical components such as the identity and access management in order to provide the basic user authentication, authorization services. In terms of the front end, we have two basic interfaces have been developed. The first one is the operator dashboards, which is a web page that provides functionalities to control road closure or lane closure of the infrastructure, and also the mobile application, which is the basic means of informing drivers and users about events, and also the basic means of providing trip planning services. One component which is which has been developed in addition within the mobile application, and which has been designed by our partner BGU, is the driver behavior analysis. So the aim of this component is to assess highway user behavior under stress. So this is based on data which are taken through questionnaires presented to end users by the mobile application. And these questionnaires include information such as socio-demographics, driving exposure, and the tendency to take risks. So based on this information, 3 support levels are extracted. So the categories of these levels are drivers that need support, that would like support, and drivers which are fine, which are cool using support. And according and based on these categories, we customize event messaging visualization in terms of coloring and in terms of showing messages when we really have to, or omitting messages when there's no real need to show messages to end users. Now regarding the specific interfaces and front ends that we mentioned previously and the users, the capabilities provided to road operators are the visualization of the road status, the road and lane management, and the calculation of average speed on a given lane segment in near real-time performance. Regarding the commuters, the drivers, as I said, we provide the trip planning and navigation, the overall awareness, and the rerouting suggestion in terms of providing pop-up messages in a navigation mode of the application. I will show you a video regarding the actual functionalities developed. What we see here is the dashboard, and in parallel also the mobile application. So users register and they log in through through the corresponding interface. Registration includes a typical username, let's say password definition, through the interface which is developed within the application. So there's no need to go to some other web page or something like that. And moreover, login is based on a typical username password insertion within the application. So by using this login, we can have personalized services provided through the app. The first time a user logs into the app, we have included the questionnaire with some essential, let's say, questions, background questions, in order to for us to extract the profile and categorize end users into the three classes that we mentioned previously, and according to each class, then messages are shown to end users. Of course, this is a process that happens only once. After the first login to the application, users go directly to the splash screen of the app, which is actually the map showing the initial position of the end user, the driver, taken through the GPS sensor of the app. So in addition to this, in the splash screen, we can use sets of, let's say, various geographical places, and also obviously use the itinerary planning services. So in this case, we see a planning that uses the Egnatia lane stretch in normal conditions through the highway. And obviously, operators can intervene to the system in order to, let's say, schedule a road closure. So in this case, that what we have, that was what you can see here. So in this case, we have the application of a road closure event, which is then disseminated to the route planning engine of the system. And obviously through the app, end users can see differentiation into the routes. Here we see that, let's say, the supplementary road, not the highway, is used as the proposal for the same, let's say, trip previously made. Also, we can see with different color coding the possibility to take a bus from Igoumenitsa to Thessaloniki with the trip that we use as an example through the stretch of the Egnatia highway. Also in the navigation mode, the event is disseminated so that users are aware of this closing. This is what we see here. In red, there's a marker which provides all this information in order for end users to know that there's some event happening on the road. And we have different color codings for different modes. So in this case, we have to walk and take the bus. So in addition to the road closure, we have also the lane closure events, which are again controlled by road operators through the dashboard. So we can click on the buttons of the dashboard and make these lanes again, insert these events to the system. Obviously, there's the status icons showing that a lane has been closed. And in addition to this, when in the navigation mode of the app, we get the notification, which you will see. And in the meantime, also the simulation engine calculates what the estimate is regarding the average speeds of the lane which is open, let's say on the stretch of the highway with one lane closed and one lane open. And this information can be visualized on both the markers shown to the end users and also the dashboard. Now, obviously, the calculations made by the engine are controlled through, let's say, some basic controls of the dashboard. So through the dashboard, we can control the amount of vehicles per hour, which typically go over the specific road, and also the percentage of heavy vehicles to light vehicles, since that also has to be taken into consideration in order to, let's say, make estimates of a given traffic speed situation over a road. So this pretty much summarizes the basic application of the module, and thank you very much.
Thank you very much, Dodoris, for that presentation. Very clear. We've now come to the end of the second part of the Resist final event. We'll now be going on a short coffee break. The coffee break will be till 5 minutes past 12. So in about 9 minutes from now. Please don't go yet. I mean, just go for the coffee break, and you're kindly asked to come back. The most interesting part is yet to come, and that will be the system validation and results. So see you in about 8 minutes time. Thank you. Times we'll be looking into the system validation and the results. We've heard a lot about the components, about the modules in the Resist system. And now we want to see how all these modules have been integrated together in performing the pilots in Greece, the T9, T11 bridge, and at the St. Petronila tunnel in Italy. Before we go into the details of the pilot results, kindly like to ask Margarita to give us a detailed inspection of the process flow. Margarita, the floor is yours.
Thank you, Oleg. Thank you, everyone. I have to you see my screen. Is this okay?
Yes, perfect.
Okay, great. So thank you, everyone, for attending. I'm Margarita Christodoulis from ICCS. Okay. So before, as Vola said, before going to the final, let's say, results and findings based on the pilot demonstrations, I may present you, let's say, how all these components that we have seen up to now can operate as a whole system and provide and exchange data and provide an holistic overview to the operator. So,
Margarita, we can't see your screen again, so I don't know whether that was intentional or not, but
is this okay now?
Yes, now we can see it. Yes.
Okay, great. Sorry for this. So let's assume that a road operator and an infrastructure has installed the whole Resist system and is in operation. So it can be, let's say, used and provide beneficial information in case of an event. So prior to the event, the Resist system provides a continuous cybersecurity assessment through the cybersecurity module. And also, in case there are already existing and fixed sensors on the infrastructure, it can also provide the monitoring of these measurements. So let's assume that we have an event in the infrastructure affecting the road. So a relevant alarm will be received by the traffic control center. And the same alarm is integrated and will be received by the Resist platform. In this case, the road operator may decide that the road needs to be closed so as to inspect the area. So all road users that may be affected by this closure will be informed through the mobility continuity application. After that, the inspection process can be initiated. So the operator prepares the mission, the flight plan for the drone, for the computer vision drone. In case the flight plan is not sufficient or correct or something is missing, the drone operator may request a new flight plan. And based on this, the drone flies and inspects the area that has been assigned to do in order to collect some raw images that are stored in the platform. Based on these images, the 3D point cloud of the infrastructure is created, and these images are processed and annotated based on the metadata from the computer vision system. And the operator can assess these annotated images and decide in case he or she may identify some defects that may be suspicious or dangerous or may affect further the infrastructure. He may decide to request a new flight so for additional measurements through the contact drone. So in this case, a new flight will be performed through the contact drone. This can be done either using manual or autonomous navigation in order to collect some ultrasonic and rebar measurements that will be used for the structural vulnerability and risk assessment of the infrastructure. Based on this analysis, and in case the operator decides that the defects that have been identified are not crucial and the road can be is still safe for use, the road can be reopened. So let's see these steps one by one. So here we have the cybersecurity assessment. This is prior to any event. The operator can log in and select the corresponding module that is integrated in the platform. In this case, the cybersecurity module. The specific organization, project, and asset can be selected, providing all relevant information about the status, the cybersecurity status, and some relevant graphs. Okay. And this is a typical, let's say, operation of the road and what the operator can see through the dashboard and what the road users can see through the mobile application. So you can see that the road is open, no issue. There's no issue in the road. So in case a driver searches for a route, he will receive the typical route using the main, let's say, road network. In this case, the Technostaff A32 motorway. So in this case, it's the creation, let's say, of the alarm. This is the back end of the traffic control center of Technostaff. So in case the operator is aware about an event, he can manually create a corresponding alarm that can be assessed later on. I will move this one. Okay. And based on this event that has been created and the same information that have been inserted by the operator, the same corresponding alarm is received by the Resist platform. So again, in case you select the CEP module, you can see in the events, let's say, tab, you can select the asset, and here you can see the event that has been created by the traffic control center. So in this case, the road operator decides to close the road so as to start an inspection process. And here you can see what the drivers will receive. You will see the pop-up. Here's the pop-up message. So the driver is requested to is rerouted, and then the alternative network is used in order to bypass, let's say, the affected area, to bypass the tunnel that is unavailable. And now the actual inspection process starts. So the operator can select the relevant module and create a new, let's say, inspection process. In this case, it's a detailed one. Okay, and he can select the exact personnel that will be assigned to perform each step. For example, the RPAS operator, the drone operator, the computer vision operator, and so on. So the inspection is created. the allocated persons have been informed and received the assignment to take part in this inspection. Sorry, we saw this. Okay. And now it's the part where the drone operator waits for a flight plan in order to know to which area he needs to fly the drone and to inspect. So the IPM operator provides the flight plan. Here you can see the description and sends this flight plan to the drone operator. Okay, the drone operator receives this flight plan. Here you can see the details of this flight plan that has been sent. Here it is. In this case, he rejects this plan because some information is missing. He also provides a relevant justification for the rejection. So the IPM operator is again aware about this rejection, and he prepares the new flight plan. Okay. He see the rejection, the justification why this has been rejected. So the new flight plan is inserted with more, let's say, waypoints and so on in this time. So the drone operator receives the updated, let's say, flight plan. In this case, he will accept it. Okay, here it is, the new flight plan. He accepts and confirms this. So based on this, we have the actual flight plan. This is the computer vision drone in order to collect raw images of the area it is assigned to do. This is an autonomous navigation. As you can see, the operator does not manually navigate the drone. He's only for a backup in case something goes wrong. So the drone follows the exact flight plan that's been defined by the IPM operator. During this flight, it collects some raw images of this area, of the affected area. After the completion of the flight plan, it lands. So when the flight is completed, the operator informs the platform, so all involved staff can be aware that this has been completed, this step has been completed. So the IPM operator receives the confirmation that this has been completed, and the images that have been collected, the raw images, are stored to the platform so as to be further processed. Through the backend, these images are processed, creating all the metadata and 3D model we will see later on. So the operator again informs the platform that this step has been completed, the storage of the processed images this time. And here you can see, based on this processing, what is the output. In this case, we have the 3D point cloud of the infrastructure. We select the relevant, let's say, module. Again. Okay. The operator is informed that all has been stored properly. So he goes to the relevant module, selects the specific inspection, and in order to see all the relevant, let's say, data collected. So here you can see the 3D model of the tunnel, this surface of the tunnel, as this has been created through the processing of the raw images that have been collected by the drone. And also here you can see the first, let's say, assessment of the defects that have been identified. So here is an example of some defects and their IDs. You can see them in a very high quality. And you can also select a specific defect ID for further information, the exact, let's say, location, coordinates, and so on. So based on this information, the operator decides that further measurements need to be performed in order to be sure that these cracks are not critical for the status of for the safety and security of the infrastructure. So in this time, he assigns the contact drone operator to perform some flight plan based on a specific defect. So the drone operator is aware about the exact coordinates of this defect. So he receives the new assignment for extra measurement through the ultrasonic sensors and that have been embedded in the contact drone. Here you can see the exact defect and the exact coordinates of this one. He accepts this mission. Okay. And he starts the flight. So here we have the second flight with the contact drone this time. This manual navigation. As you can see, the drone takes off and attaches the wall, the surface of the tunnel, to the location of the exact defect that it has been assigned to inspect. So it attaches. And here you can see the footage of the sensor and also the camera that has been embedded in the drone. Here in the below part, you can see the ultrasonic sensor moving and scanning this area of the defect. Every time you see the light flashes, a new measurement is taken. Okay, so it scans the full area of the defect, measuring the crack width and depth and so on, collecting all these necessary measurements. And when all measurements have been taken, it detaches the wall and safely lands on the ground. Here you can see the same process, but using an autonomous navigation. This is fully autonomous navigation. I will forward it. Here you can see the analysis and the exact location of the drone, the relative position based on the infrastructure. Here you can see the location of the drone as close enough to the wall. Again, it attaches the wall, gets the necessary measurements, and then it safely lands on the ground. Okay, so based on this new measurements that have been collected, the operator can move on to the structural vulnerability and risk assessment of the infrastructure. Here you can see, you can select the exact infrastructure and specific asset, in this case, the Central Petronila tunnel. Here you can see the model that has been created, the exact, let's say, area that has been affected. And here you can see the exact locations where some defects have been identified and what is their status, the relevant diagrams based on the measurements that have been performed and the processing of these measurements. And also here you can see the analysis and some details about specific cracks. Here you can see details about the width, depth, and so on. And here the relevant annotated images. And so here you can see in more detail, more high quality. Okay, so based on this analysis and this assessment, the operator can be aware about let's say how critical the crack may be, and if this needs to be, let's say, maintained as soon as possible, or is something that can be done in a later phase. Since these defects and these cracks were not considered as critical or let's say that may affect the road and the infrastructure, let's say structural integrity, the operator decides to reopen the road to give it back to the drivers to normal operation. So here he opens the road again. Here you can see the notification will be, the alert, let's say, will be deleted, okay? And in case a driver researches for the same route, he will receive the typical, let's say, the typical route using the infrastructure and the tunnel as this has been given back to normal operation. So this from my side. Thank you very much. I think we can move on to the actual results and the perspective of the end user of the project. So thank you, everyone. Vola, back to you.
Thank you. Thank you very much, Margarita. And just as Margarita said, the last two presentations will be about the pilot results from Greece and from Italy. And we start with the T1911 bridge in Greece. Panayotis, the floor is yours.
Thank you, Holger. Good morning from Thessaloniki, Greece, Egnatia Odos. I will share my screen. So I will present the results and the comparison results from the first pilot of Resist, which took place on TAF9 bridge in northwest Greece, in Egnatia Motorway. Of course, our strong motivation in participating in this Resist project was that we really need to minimize the impact of extreme events for our critical infrastructures, as we have to manage, inspect, and maintain 1,200 bridges, as well as other structures in the 1,000 kilometers of the Egnatia Motorway, and to provide seamless mobility and safety of the users. So we need to increase the resilience of our infrastructure, and according to our experience since 2008 in European projects, we can provide practical real scenarios for validating and field testing research projects and research products as this of Resist.
Excuse me for the interruption, but we can still see the first slide of your presentation, not the full presentation mode. So you may swap the screens.
Now? No.
No. Maybe you should share the whole screen instead of the presentation.
Yes. Let's try again. Now, I think it's okay, yeah?
We can still see the first, okay, now it's great, yes,
okay,
great.
Yes. So I'm sorry for this. So what we selected TAF9 bridge. It is an area really prone to earthquakes as well as landslides. So it was problematic from the very construction phase. And we selected DAF9 bridge as was really demanding. We had to cross a difficult obstacle, a ravine, a deep ravine, and the bridge was very costly and demanding, a sophisticated design and construction, and also inspection and maintenance is well demanding, as it is really non-accessible by only with mechanized platform. The main risk of the DAF9 bridge is high seismicity, as it is for any Greek bridges. The active landslide of the areas where abutments are founded, high precipitation that we found out that is affecting the underground water pressure and the regime of the landslide, and the corrosion induced by the frequent use of the icing salt, as we are in a mountain area and we have a long winter maintenance period. You can see the DAF9 bridge area and the area A and area B are two active huge landslides that have to be stabilized in order the end part of the bridge, the foundation of the bridge, to be also stable, which with a landslide with a big front, 700 meters, and a very deep, 450 meters. And the stabilization measure, you can see the characteristic longitudinal section of the landslide. You can see here the counterweight where the foundation of the bridge was seated. At the top left, you can see the drainage tunnel that we have also to construct in order to relax the underground water pressure. And finally, even after a lot of expensive measures, the active landslide still was active, and we had also to unbox the river in order to retain both slopes to stop sliding. You can see here the successful the success of after the completion of the stabilization measures. As you can see that the landslide rate was really practically negligible, and we hope that this is still a reality here, but we have to inspect and to combine all the proper measures in order to be sure. So, operators' conventional efforts. It is a bridge that is more than any other bridge tested and analyzed. So we made also for the purpose of the RESIST project visual inspections, geotechnical monitoring with inclinometers and piezometers, structural monitoring with movable and permanent network, not catastrophic testing. You can see here our arrays of accelerometers, the identification of the dynamic characteristics of the bridge. It was a reference line in order to be compared with any type of vibration monitoring, or also from resist monitoring in the future. An extra fine 3D model with soil and bridge interaction in order to update the model, the dynamic model of the bridge. And here you can see that the bridge, of course, it was really stiffer than it was designed. And this is very basic to start the life of the bridge with a monitoring and updated of the real dynamic characteristics. Then we installed a permanent strain monitoring system that also was operated during the resist training and the resist trials. So the basic scenario for the resist pilot test was if a severe seismic event with a big gravity acceleration more than 0.2 of gravitational acceleration may trigger the stabilized landslide areas where the bridge edge span are supported. You can see here that in that case, you have the bridge end span to perform as a country level, and this could be catastrophic after the exceeding of a limit. So step by step and activity by activity, what was tested, and I will present now. First of all, we in parallel inspect by touch and by the use of this expensive and time-consuming and not very safe for the personnel of Egnatia gantry, special gantry with a basket to give us access at the other side. We spent 2 and more days to make a detailed by touch inspection. In parallel, we compared with the very successful and very fast operation of a drone that was scanned and fastly in detail by a distance of no more than 1 meter, inspected all the concrete surfaces, non-acceptable concrete surfaces of the bridge superstructure and of the piers. Second, it was geometrical survey. With total station and leveler, we have to measure the relative deformed altimetry due to temperature, as well due to imposed loads that I will show you later, as we also organized and executed load testing. And at the same time, by resist side, we had the photogrammetric and laser scanning digital representation, as it was also demonstrated in the previous presentations. Recording, representing of visual data. This is something, a very difficult and time-consuming and labor-consuming task. Here you can see that we have all the data and findings of the visual inspection to be categorized, detected, interpreted, and finally presented, mapped in CAD drawings. This is a difficult job, and what is from resist side, the direct storing of all the data to the resist platform, and then classification by artificial intelligence. So here you can see some results from manual inspection and some good results from the vision system and the artificial intelligence. Either this is a detection of cracks not very deep in the surface of the superstructure of the TAF9 bridge, or it was surface defects, as you can see here, a combination of corrosion stains and efflorescence that were successfully also detected as location, area, and type of defect from the artificial intelligence developed here for the purpose of the resist. Structural monitoring is an activity that it is extensively used by Egnatia almost in every type of assessment. So here, in strengthening our permanent strain monitoring system, we also deployed our movable accelerometers for the purpose of resist. And at the same time, successfully, the UAV installed 2 vibrators, 2 accelerometers, 3 accelerometers that also were operated and measure vibration, ambient vibration, or vibration induced by traffic and wind. Not catastrophic testing, either by Egnatia using conventional portable ultrasonic device, which needs a lot of time to be installed and measure and needs at least 2 persons to do it. And at the same time, a continuous measurement from a specific ultrasonic device on board of a UAV, and then by rolling on the surface of the concrete, took a lot of surface velocity propagation measurements of the surfaces of the bridge. Analytical assessments of the effects, consequences of the damage. In Egnatia, of course, we are doing and we did for the purpose of resist, manual structural analysis on purpose, not establish a direct relationship between measured and analytical predicted parameters. Always there is a subjectivity, and there is also a lot of time required for this job. What from resist, there was an automatic use of deterministic probabilistic analysis results that, of course, we are going to show in the 9.2 final deliverable, and which is also open for everybody. And supplementary load testing, it was organized and executed for the resist project. You can see here a lot of arrays of pre-weighted tracks that were imposed on the mid-span of TAF9, and in order to artificially loading up to the limit state value, serviceability limit state of the bridge. And then by a total station from our side and by our strain monitoring network, we in parallel measured the performance, the response of the bridge during the continuous steps of the load testing. What about resist? There was the vibrator, and there was also the deterministic module that was assessed and analyzed the response results that were given by Egnatia. You can see here a characteristic image of the final and most demanding phase of the load testing. And of course, there is always a risk during load testing, even in a new bridge. You can see in this top right diagram that the analytical prediction by Red was well enveloped, the measured, so the bridge was stiffer and integrated. So I finalize my presentation by component comparison and results. First of all, UAV-based visual inspection of non-accessible structural functional elements of TAF9 bridge. You can see the basket, the unsafe and time-consuming procedure, and the very easy and fast scanning inspection by the drone in a very non-accessible bridge. All defects that were detected by the parallel visual inspection of Egnatia Odos were successfully detected by the visual system based on productive visual scanning of UAV. Position, type, area of various defects were found similar and with the same accuracy as of the conventional inspection. What about time required for inspection? 500 square meters of concrete surface per hour of UAV operation, needing only just one pilot, and from Egnatia, 150 square meters of concrete surface per hour of using mechanical platform, 2 persons for using crane and 3 inspectors. UAV-based non-destructive testing of non-accessible structural functional elements in direct surface ultrasonic propagation velocity was successfully measured by the special UAV with an ultrasonic device rolling on the concrete surface of the bridge. What was the time required for non-destructive testing? Resist 100 continuous measurements per hour of UAV on board ultrasonic device. Comparing with 20-point measurements, it's impossible to have continuous measurements. We have to install and reinstall again and again for covering different sections and different measurement points using mechanized platform, as we don't have access and a lot of personnel. 2,000 to 3,000 meters per second was the surface velocity results in both activities, with a remark that surface velocity propagation measurement, it's not the most reliable way of not destructive tested, but it was the only possible for this type of box beam superstructure. UAV-based crack depth measurement of non-accessible cracked concrete was again a successful demonstration for resist, as there was indirect surface laser continuous measurement of distance of UAV arm rolling across the concrete surface. And here we had a very fast response, and the result was 10 to 25 centimeter crack depths measured from both measurements. Direct assessment of visual non-destructive testing, data collected. So at the end, a lot of findings, a lot of measurements. What we do, Resist proved that we can directly post-inspect, categorize post-inspection findings and characterize defects. Represent mapping this defect and assess the results and reporting. So this is the most impressive comparison result, as for Resist, we have a direct near real-time assessment and reporting using one user of Resist platform and maybe one engineer. For Egnatia, we needed 2 days for processing, interpreting, reporting, representing in CAD drawings and rate the condition of inspection data. 1 engineer for CAD drawings, 2 engineers for reporting, processing, condition rating, not real time, but in office. Similar quality of assessment results. You can see here some results of the defect mapping that it is really needed as the end result, the end product of any inspection, and the defect categorization, which was really successful in both activities. UAV-based vibration monitoring, installation of ultralight accelerometers on the vertical concrete surface. Here again, we have from Resist side direct real-time continuous acquisition, while in Egnatia we have a limited acquisition of a few 10 minutes time histories recorded by manual triggering, which is of course a handicap. But to be honest, from the moment our really demanding in labor and in time. Servo accelerometers are still a lot of more accurate from any other type of device. And some screenshots from the strain data that were transmitted to the resist platform. You can see here a characteristic plateau of the strain evolution from the before load testing and the 4 steps of load testing, with the increase of the strain, which again was well lower than the predicted from the analytical models. And of course, in D9.2, we are also expecting from the relative partners to analytically give us results from the successful assessment from their module. This is all from me. Thank you very much.
Thank you very much, Panayotis. Very, very interesting presentation, and the analysis and results indeed very, very impressive. Thank you very much for that. We go to the last presentation, the second pilot in St. Petronila Tunnel. And before we do that, I just want to say, apologies that I didn't mention this earlier, but after this presentation, I'll be kindly asking us to put on our cameras so that we can just take a group picture for those that can do that. Obviously, we encourage everyone that can do that, but if for one reason or the other you are not in a position to do that, that's also understandable. So once again, immediately after the last presentation from Saverio, we'll ask you to kindly put on your cameras just for a group picture. Thank you. Over to you, Saverio.
Thank you. Can you see my screen?
Yes, please.
Thank you. Good morning, everybody. I am Saverio Mercurio from Technosita, the ICT technician from Regis project. After Ignatia results and explanation of Panagiotis, I'm going to summarize results and added value from the point of view of a motorway manager. This is a quick recap of the area in which Resist project insisted. The A32 motorway is divided into sections. The first one begins from Rivoli to Susa. It's long 36 kilometers, and it has 2 driving lanes and 1 lane for the emergency. The second part, mostly constituted by tunnels, is long also 36 kilometers and has 2 driving lanes in the 2 directions without emergency lane. There are 2 tolling stations, Avigliana and San Bertrand. The Susa Valley has quite extreme weather conditions, very cold in winter and very hot in summer. The A32 control center is located near Susa, while a control center for the international tunnel is long 13 kilometers, is situated in Bardonecchia, inside the city's offices. The highway runs through a mountainous region with numerous valleys and tunnels, posing a very challenging scenario for robotic technology. We had 2 pilots. The first one was the Milor Viaduct, that is a 2-way bridge for each direction. It's a 40 years old infrastructure, length about 400 meters, and this is a mixed steel concrete structure affected by oxidation and cement deterioration. The second pilot has been the Santa Petronila Tunnel, a regular size highway tunnel used as escape way from a longer tunnel, 5 kilometers on the motorway. It's length about 600 meters, and normally it's close to traffic, and it is safer for testing simulation. This tunnel was extremely useful to test drone flight capability in absence of GPS satellite signals. Our infrastructures in the motorway are affected by these main defects. Regarding the bridge, we have a lot of oxidations. The bridge is built in weathering steels, so there is a superficial oxidated steel that is useful to protect the infrastructure itself. But if the corrosion runs too much, this begins to be dangerous. Also, we have cracks and concrete deteriorations that cause the exposure of the reinforcement bars. We have to say that the physiological state of surface degradation and corrosions of the reinforcements is due mainly to the effect of atmospheric agents, and in particular, in circumstantial cases, to constructive defects associated with the executive complexes related to the time of the realizations. This bridge was built in the early 80s. A lack of attention in the concrete casting phase, together with an insufficient concrete cover, are the most frequent causes of degradation, which, over time, can identify areas more exposed to cortical deterioration of the parts of the work. These works of art are undergone extraordinary maintenance focused on the cortical restorations of the degraded structural portions, with the aim of restoring the original integrity of the work of art through restoration intervention with special mortars and reinforcement with the fiber reinforced composite materials. Regarding tunnel defects, the main defects can be collapse of concrete from the roof. That happened also in Genova in a recent time. And wall cracks and water percolation. Water percolation are also big and dangerous defects, as water can affect electronic installations on the walls of the tunnel. This is a recap of the main results and added value of resist. We will see in details afterwards. Newer passport in addition to visual inspections, lower costs, new wireless vibration sensors, reductions of destructive infrastructure tests, concrete drills, communication robustness enhancement and cybersecurity. Last but not least, improvement of predictive maintenance by a better quality of diagnosis. Resist gave us safer inspections. The integration between man and machine, human factor, manufacturing in which robotic devices come to rescue of human components to make work less demanding. As you can see in the picture, we had an incident in which the gasket collapsed down the bridge with injured people. Of course, also hanging men with ropes is a danger activity of inspection we don't want to see anymore. So drones and unmanned aerial vehicles are finding increasing usage in bridge and tunnel inspection system market, through enabling users in collecting inspection data effectively in substantially less time than the traditional systems. Additionally, drones aid in surveying hard-to-reach areas of the infrastructure by capturing high-definition images and visual data of bridge components, eliminating the requirements of manual labor and danger labor in process. Also, using drones, we have cost reductions for inspections. To resist outcomes, we have a tunnel inspection drone and bridge inspection drones. Against the visual inspection traditional type that is performed using at least 2 trucks with people examining the upper zone of the tunnel and the lower zone is costly. Summarizing, we have in resist about 7,000 euros for traditional inspection with no test, but with the RPAS inspection, with all sensor and assessment, we have about 4,000 euro of cost, so much less. The accuracy of the inspection also is high, removing the operator away from the traffic and reducing the way of fatal accident and injuries during inspection. Another important benefit from RESIST project is the development for a new kind of wireless vibration sensor. As you can see in the picture, the device is very small compared with the old wireless sensor installed under the bridge. We are supposing that on a larger production scale, they will be less expensive. Moreover, the installation is easier and faster. The sensors can also be installed with a drone. Given that fixed sensors are recommended for a constant monitoring service on the motorway, those new sensors are expected to be very useful when technicians have to perform structural accelerations and vibrations recordings on bridges that are not already equipped with any device. The difference between all the new sensors is visible. It should be noted that constant monitoring is essential, but wireless sensors require less work to be positioned, facilitating a faster data collection. This slide shows another important success of the project. This innovation consists in the capability to use ultrasonic waves to detect the depth of the cracks. This method, in many cases, reduces the number of destructive perforations of the infrastructure. Another positive effect in the saving of human effort in the drillings activities that produce dust and noise. Regarding communication enhancement, immediately after the dramatic collapse of the bridge in Genova 2 years ago, the lack of information about alternative roads caused a dramatic congestion with enormous economic and social damage. Another key point of RESIST project is communication enhancement. Rerouting suggestions and alternatives are very important part of the platform. The applications permits to set up navigation and to receive traffic information in real time. Most part of modern cars supports direct interfacing with smartphones, able to receive additional information that can help users to avoid getting trapped on motorway inside tunnels. Thanks to computer vision, we also get data of other defects affecting infrastructure. Speaking about the forecasting of maintenance activities, we can say that the improvement of the predictive maintenance by better quality for diagnosis is reached through photogrammetric and computer vision system. With the structural assessment and damage prediction representations, inserted in the management software, the intervention priorities can be quickly managed as the system shows which part should have the restoration intervention priority. In terms of safety, moreover, by ordering them by decreasing severity of the defects, this classification allows the operator to immediately define the structures that present real dangers and at the same time to make targeted decisions to each individual work. In terms of risk management and cost containment, it is very important to start intervening on the parts that have higher degradation paths. Of course, we are not only dealing with the cracks on the structure, but through computer vision, we have an input that can have the output, the fluorescence and corrosion states indications as well. The integration environment adds high value of the project because it groups all the functions in a single environment, avoiding the problem of achieving the same results through unrelated softwares. The integration itself is time and cost saver for professional users in the control centers of CTAF. Among the many advantages of this solution, TechnoCTAF, as an end user, sees the possibility of implementing alarms in the monitoring sensor, detect vibrations above the standard vibration level. If after verification the alarm is real, this is a fundamental fact because it allows the emergency teams to activate all the operations to be carried out in the event of an emergency to save lives from probable disasters. From the point of view of maintenance cost, performing maintenance on infrastructures is the most expensive task for motorway concessionaires. The Estesis platform helps infrastructures maintenance cost optimizations. It is very important to have a correct balance between preventive and corrective maintenance operations. The graph shows the optimal area that is identified by the correct balancing between preventive and corrective maintenance. The platform helps to correctly identify this balancing. As you can see, we can, if we have excess preventive maintenance, we have a very high cost. Insufficient preventive maintenance causes low infrastructure health, while correct maintenance area give the balance from good health of infrastructure during his life, expected life. For the point of view of cybersecurity, the project has given an important contribution to increase the isolation of data networks. For the management of technological systems, we have taken steps to reinforce the isolation from the internet. The solution allowed us to interact with external platforms such as Resist without risking intrusion and hacker attack. Thank you for your attention.
Thank you very much, Saverio. Thank you for the closing presentation in the system validation and results session. Before we go further, can I kindly ask, just as I said earlier, for us to put on our cameras, please, just for 1 minute, if you can. If you can put on our cameras so that I and my colleague will take the picture. Just a minute. Okay, thank you for that. Angelica, let us know when you're ready. Thank you for that. Thank you for another 30 seconds. And Angelica, let me know once it's done.
Yes, thank you very much. Yeah, thank you very much.
It's done. Good. Thank you very much. And apologies that we've overshot our time, but indeed we have so much to present. It's always not easy to do this, a 46-month project to present in 3 hours, but I think we've been successful in doing that. However, I would still like to give anyone the opportunity, everybody the opportunity to ask questions, or to make comments, well, most especially from our stakeholders. I don't expect any member of the Resist project to make any comments now. It's too late for that, but peradventure there are comments or questions from our stakeholders. Please, you are very much welcome to do so. I give the last chance Unfortunately, our project officer had to move to another meeting, but he thanked us for the invitation and for the good attendance. I don't see any hands raised up, neither do I see any comments in the chat. In that case, I would kindly ask ICCS for the closing remarks. And from my side, thank you very much for the participation. And over to you. I don't know, is that Angelos that will give that, or Margarita?
I don't know if Angelos will like to make a final, let's say, a closing to this meeting. From my side, at least, I would like to thank all attendees for their presence in our final event. I think this was a quite, let's say, complex project, and for this, I would like to thank all project partners for their efforts and the work done. The project has almost ended, actually next week, but we will keep, let's say, disseminate our results and exploit them. And everyone stakeholder that is interested can also meet us in the following TRA conference next November in Lisbon. So yes, I would like to thank everyone for this project and for this event. Vola, thank you personally for the preparation. And yes, this is it from my side. I don't know if anyone else would like to make a closing, let's say, remark.
Okay.
Yes, no.
Thank you very much to everyone, the project partners, to all those that have taken part in all our events and this last event as well. It's been a very long, interesting journey over the past 46 months, and I wish you all the best and enjoy the summer holidays.
Thank you all. Bye.
Thank you.
Thank you very much.
Bye-bye. Thank you.
Thank you.
Bye.
Bye.
Thank you.
Bye.
Thank you. Bye.
Hi, Margarita. Hi, John.